Welcome to our quantum deep dive. Today we're plunging into, one of the most fascinating and honestly probably the most critical topics in quantum computing right now. Quantum error correction.
Absolutely critical.
Yeah. I mean, if quantum computers are going to move beyond just, cool lab demonstrations and actually revolutionize things like medicine, AI.
All those big promises we hear about.
Right. Then QEC is like the foundation, the pillar they absolutely need. It's kind of the unsung hero making it all potentially work. And our mission today is really to unpack why it's so essential. Not just nice to have, but a must-have for getting these things from theory to, practical tools. We're digging into an insightful essay today by Jorgo Schneppat titled Quantenfehlerkorrektur Schlüssel zur stabilen Quantenwelt. That's our main source here.
Exactly. And it's so needed because quantum computers, they hold this incredible promise, don't they?
Yeah.
Solving problems classical computers just can't even begin to tackle. They could really change the game in so many fields. But, and it's a big but, there's this fundamental hurdle, this fragility that needs some really ingenious solutions. That's the challenge.
Okay, so let's unpack that quantum paradox then.
Yeah.
Immense power, but extreme fragility. When we talk quantum, the first thing is usually qubits. Unlike our classical bits, 0 or 1, qubits can be, both at the same time, which leads straight to superposition. Superposition it's like the qubit exists in multiple states at once. It's not just 50-50 either. Mathematically, it's described with these complex numbers, alpha and beta, for the 0 and 1 states.
And those complex numbers are key. They have amplitude and phase. The phase part is crucial for interference, which is where quantum algorithms get a lot of their power. It allows for this massive parallel computation, sort of exploring many possibilities simultaneously.
Right. That phase information is vital. And then there's the other really mind-bending concept, entanglement.
Ah, yes. Einstein's spooky action at a distance.
Exactly.
Yeah.
It's this weird, deep connection between qubits. Measure one, and you instantly know something about the other, no matter how far apart they are. Like they're linked.
Perfectly correlated. It's represented by things like the Bell state, where you have this inseparable combination of, say, 0, 0, and 11. And this is absolutely fundamental for efficient information processing in quantum computers. It allows them to tackle huge problems.
So you've got superposition, entanglement, incredible power. But you said this is also the source of the fragility.
That's the paradox, precisely. These very quantum phenomena are incredibly delicate. The biggest enemy is something called decoherence.
Decoherence, okay.
Yeah, it's basically the process where the qubit loses its quantumness, its superposition or entanglement because of interactions with its environment. Think tiny vibrations, stray magnetic fields, even cosmic rays.
I'm trying to keep a soap bubble perfect in a hurricane.
That's a great analogy. Any little disturbance can pop it. The time frame for how long a qubit can maintain its state is called the decoherence time, or T2, and for many systems, it's frustratingly short.
Okay, so these environmental interactions, they cause errors. What kinds of errors are we actually talking about?
Well, broadly, we can think of a couple of main types. First, there are bit flit errors. Pretty straightforward, a qubit that should be 0 flips to 1 or vice versa. Like an X operation acting on it.
Yeah.
Similar to a classical bit error.
Okay, that makes sense.
But then you get the purely quantum ones. Phase flip errors.
Yep.
This is where the sign in the superposition changes. So like a state that's an equal mix of 0 and 1 might flip to being 0 minus 1. A Z operation does this.
Ah, affecting that crucial phase we talked about.
Exactly. It's subtle. You wouldn't see it if you just measured 0 or 1, but it messes up the quantum interference needed for algorithms.
And I guess you could have both happen.
You certainly can. We call those combined errors, or sometimes depolarization. It's like a mix of bit flips and phase flips, maybe caused by a Y operation, which is like applying X and Z together. These are often the trickiest to deal with.
Right, so this brings up a massive problem. In classical computing, you just make copies of data for backup, for error checking, redundancy. But quantum mechanics has that famous rule. You can't just copy a qubit, can you?
You absolutely cannot. That's the no cloning theorem. It's a fundamental principle. You cannot create an identical copy of an arbitrary unknown quantum state. It's not a technological limit. It's baked into the laws of quantum physics.
Wow. Okay.
So yeah, that throws the classical playbook for error correction right out the window. You can't just make 3 copies and vote like we do classically.
So if you can't copy, and you can't even look at the qubit directly without destroying its state, how on earth do you fix errors? This sounds impossible.
It does sound impossible. But this is where the sheer ingenuity of quantum error correction, QEC, comes in. It's really quite clever.
Okay. I'm intrigued. How does it work then?
The core idea is syndrome measurements. Instead of measuring the data qubit itself, which would collapse it, you use extra qubits, called ancillary or auxiliary qubits.
Okay.
You entangle these ancillary qubits with a group of data qubits in a very specific way. Then you measure the ancillary qubits.
So you're measuring the helpers, not the main data.
Precisely. The outcome of measuring these helpers gives you information, a syndrome, about what kind of error might have occurred and where it occurred, on which data qubit, but crucially, it tells you nothing about the actual quantum state of the data qubits themselves.
Like a detective finding clues without disturbing the main evidence.
That's a perfect way to put it. You learn about the error, the symptom, without learning about the patient's confidential information, which is the quantum state. Once you know the syndrome, you know what correction to apply, maybe an X gate, a Z gate, or whatever, to fix the error, again, without ever needing to know the original state.
That is incredibly clever. So using these syndromes, how did people first figure out how to actually build codes around this? The essay mentions the Shor code.
Yes, Peter Shor's 1995 code was the breakthrough. It was the first complete QEC code. It uses 9 physical qubits to encode one single logical qubit that's protected from errors.
9 qubits for one. Wow.
Yeah, it's resource intensive. The basic idea involves encoding the qubit state 3 times to protect against bit flips, and then encoding each of those copies again in a clever way using phase relationships to protect against phase flips. It handles both types of errors. Monumental theoretically, but 9 to 1 is a high cost.
Understandable. So people looked for more efficient ways.
Definitely. Progress came quickly. In 1996, Andrew Steen developed the Steen code. This one is more efficient. It uses 7 physical qubits to protect one logical qubit.
Better. 7 instead of 9.
Right. It's based on classical error correction ideas, specifically Hamming codes, adapted for the quantum world. It uses a concept called stabilizers to define the code space and detect errors. Still complex, but a step towards practicality.
Okay, sure, Steen. But the essay really highlights the surface code as maybe the most promising for the future.
It does, yes. The surface code is seen by many as the front-runner for building large-scale, fault-tolerant machines. It's a type of topological code.
Topological. How does that work?
Imagine arranging your physical qubits on a 2D grid like a checkerboard. The logical qubit isn't stored on any single physical qubit, but rather in the collective topological properties of this grid. Errors appear as localized defects or excitations on this surface.
So the information is spread out, more robust to local problems.
Exactly. Detecting errors involves measuring properties around plaquettes or vertices on this grid using ancillary qubits to get syndromes. The key advantage is its high fault tolerance threshold. It can tolerate a relatively high physical error rate, and it seems easier to scale up just by making the grid bigger.
Makes sense. So comparing them quickly based on the essay's points, Shor is 9 qubits, robust but costly. Steen is 7 qubits, more efficient, maybe a bit complex. Surface code is variable qubits, needs a grid, but has high tolerance and scales well.
That's a good summary. And remember, they have different hardware demands too. Shor and Steen might need really high-quality individual qubit operations. The surface code needs that grid connectivity and the ability to do lots of these local syndrome measurements reliably. It's a trade-off.
Okay, theory is one thing, but are these actually being used? What's happening in the labs with the big players?
Oh, yes. They're definitely being implemented and tested. IBM Quantum, for instance, uses superconducting qubits. They showed significant error suppression, not full correction yet, but reducing errors using a small code, I think it was 5 qubits, back in 2021. They're heavily invested in surface code variations for their roadmap towards 1,000-plus qubit systems.
And Google with Sycamore.
Google, too. They also use superconducting qubits, and the surface code is central to their strategy. They achieved that quantum supremacy milestone, and they've also published work demonstrating syndrome measurements and error detection, moving towards correction. Their goal is massive scaling, eventually millions of qubits.
Okay, so superconducting seems big for surface codes. What about other types, like ion Q?
Right. Ion Q uses trapped ions. A key advantage there is that ion qubits naturally have much longer coherence times. They're less noisy to begin with.
So maybe they need less overhead for QEC.
That's the hope, potentially. They're exploring QEC too, and the longer coherence might allow for more complex operations or perhaps require fewer physical qubits per logical qubit compared to noisier platforms. Then you have others like Rigetti, various startups looking at different qubit types, hybrid approaches. It's a very active field.
It sounds like there's real progress, but we're not quite there yet with fully corrected machines.
Not yet. We're firmly in what's called the NISQ era, noisy intermediate scale quantum. Noisy is the key word. Errors are still a major limitation.
And the challenges are pretty huge, right?
Oh, definitely. First, the physical qubit error rates themselves are still too high. Every gate operation, every moment the qubit just sits there, it risks an error. Second, the resource overhead we talked about needing potentially thousands of physical qubits for one logical qubit is enormous.
Thousands.
Yeah.
That's staggering.
It is. Third, building chips where qubits can easily talk to many neighbors, which is needed for codes like the surface code, is hard. Connectivity is limited. And fourth, especially for superconducting qubits, you need those extreme cryogenic temperatures, near absolute zero. Scaling that up to millions of qubits is a massive engineering challenge in itself.
So given these hurdles, what are the main strategies researchers are pursuing to get past this NISQ stage?
Several key directions mentioned in the essay. One is building inherently fault-tolerant qubit architectures, trying to make the physical qubits themselves less prone to errors from the start.
Like the Majorana qubits Microsoft is pursuing.
Exactly, that's a prime example. The idea is that their topological nature might offer built-in protection against certain kinds of noise. It's still very much research, but it's a potential game changer.
What else?
Improved material science is huge. Finding better materials, fabricating devices more cleanly, using nanotechnology, anything to make the qubits more stable and extend those coherence times, T2. Even small improvements here can have a big impact.
Makes sense. Building better bricks.
Right. Then there's error mitigation. This is different from full QEC. It's techniques you apply during or after a calculation on current NISQ devices to reduce the impact of noise, maybe by running circuits multiple times and extrapolating to a zero noise result, or canceling out known error types statistically. IBM and Google use these a lot.
So like a software fix for the hardware noise.
Sort of, yeah. It helps get better answers from today's machines, but it doesn't scale like true QEC for really hard problems. And finally, exploring hybrid technologies, maybe combining different types of qubits or quantum processors with classical ones in smart ways to leverage the best of both worlds.
Okay, so it's a multi-pronged attack on the noise problem.
Absolutely. It has to be.
So wrapping this up, the core message really seems to be that quantum error correction isn't just some technical detail. It's fundamental. It's the bridge we need to cross to get from the theoretical power of quantum computing to actually using it for, world-changing applications.
Couldn't have said it better. Without robust QEC, scalable, reliable quantum computers capable of solving truly impactful problems likely remain out of reach. It's that essential.
It really sets the stage for what's needed next.
It does. And while, fully fault-tolerant quantum computers are still some way off, nobody knows exactly how long the progress in QEC is undeniable. It's steadily advancing, paving the way for this huge shift. It makes you think, doesn't it? Consider this for a moment. What kinds of possibilities, what new frontiers in science or technology do you think might open up if we truly conquer these error correction challenges? What becomes possible then?
That's a fantastic question to leave us with. The potential is just
immense.
Well, we hope this deep dive into quantum error correction has given you a clearer picture of why it's so vital and where things stand. Our thanks again to Jorgo Schneppat for the essay that guided our chat today. If you want to explore further, you can check out schneppat.de. Thank you so much for joining us on the deep dive, and we'll catch you on the next one.